Hello and welcome to our lesson on the limit of a function. This is section 2.2 from our Calculus 1 course. Let's get started. In this lesson, we're looking at the limit of a function. We're going to start with the intuitive definition of a limit. This is copied from our textbook. It says, suppose f of x is defined when x is near the number a. This means that f is defined on some open interval that contains a, except possibly at a itself. Then we write, and this is the notation you need to understand. So what this says, it says the limit of a particular function as x approaches some value equals L. Or it could be read, the limit as x approaches some value of a particular function equals L. So just a couple of important things to note, that a is an x value because x is approaching a, so a is going to be an x. F of x means y, so L is going to be some y value. One of the key words here that we see is arbitrarily. That means pretty much as close to L as you want to get. If we make the values of y arbitrarily close to L, as close to L as we like, by restricting x to be sufficiently close to a, on either side of a, but not equal to a. So let's look at an example of what this is trying to say. Here we have the limit as x approaches 1 of x minus 1 over x squared minus 1 is a half. We can see this if we examine the graph. Here we have our function, and we can see that as we approach 1 from either side, the graph, or at least the y values of the graph, are approaching a height of 0.5. So we say as x approaches 1, y approaches a half. That is the basis of a limit. What is y approaching as x approaches some value? Now, to demonstrate how you would actually solve a problem related to limits, we have an example that says the limit as t approaches 0 of this rational function. We want to estimate the value of the limit. In other words, we want to know what is y approaching, what is the height of the graph approaching as t approaches 0. And we can do that by doing a table of values. So we're going to make a table where we're going to choose t close to 0 approaching from the left and the right. So if we approach 0 from the left, that would be coming in from the negative side, and we could say maybe negative 0.01. That's pretty close to 0. And then if we get another value even closer, negative 0.001, I'm going to use two double bars there to indicate that we're skipping over 0 and then going to come in from the right. And it is a good idea if you're symmetric. So these values here would be equidistant from 0 on either side of 0. And using 0.01 as our other value, now what we need to do is calculate the function values of with these t values and see what the height is approaching. All right, here we go. With our Casio, plugging in the square root of, negative numbers need to go in parentheses. So we have negative 0.01 squared plus 9, move out from under the square roots, minus 3. And then again in the bottom, in the denominator, negative numbers need to go in parentheses. That is also squared. And we get a y value of 1.6, almost repeating. So let's write that down, 0.166. I'm going to put 3 sixes to indicate that that almost repeats. And then if we edit our calculation, adding another 0 for the next value of t, this should give us an even better approximation of what the y is approaching. And can you see that that appears to be 0.16 repeating? So again, I'm going to write 0.1666. And so as we approach 0 from the left, it appears that we are approaching a rational number of 0.16 repeating. Now we need to check that from the other side. So editing our inputs and evaluating the function at 0.001, we get the same value. So 0.1666, it appears to be repeating. So I have a pretty good idea that this one is going to be symmetric, approaching from the right. We can see that the limit is going to be 0.16 repeating. Now it would be really nice if we knew the fraction for that. Remember that repeating decimals can be represented as fractions. And so I'm going to give you a technique for how to convert repeating decimals to fractions. Let's start off and say that our answer, it's not really an x, let's say y equals, since it's a y, is 0.1666. I'm going to put ... to indicate that repeats. And then what I want to do is I want to multiply by an appropriate power of 10. And what I mean by appropriate is the number of digits that repeat would indicate the power of 10 that I use. So we can see that it is only one digit that repeats. The 6 is repeating. So I'm going to multiply both sides of this equation by 10. So on one side I get 10y. On the other side, if I multiply by 10, that would simply move the decimal one place, giving me 1.6666 repeating. And then I'm going to subtract. 10y minus y is 9y. If I subtract over here, from here on over, all of these 6's are going to cancel, giving me 1.6 minus 0.1, which is 1.5, and dividing both sides by 9, and using my calculator to do 1.5 divided by 9. Again, this is another advantage to using the Casio, is it's going to convert that to a reduced fraction for me. So I can see that y is 1/6. And that would be the limit as a fraction. So here we have the correct answer using bar notation. And then here we have the answer as a fraction. Now, if you've ever had me as a professor, you know that I love Desmos. So what I have done here is input the function that we just evaluated the limit of into Desmos. And we're going to verify our answer graphically. So we were looking at, as in this case, I've used x. As x approaches 0, what does y approach? And on Desmos, if you graph the function, you can actually click and drag and see what happens to your y values as you approach a particular x. So if you can see, if we come in from the left, see those y values are approaching 0.1666 repeating. If you notice what happens when we get to 0, the actual graph is undefined because you can't have division with 0. And guess what? The limit doesn't care what happens at 0. The limit only cares about what happens as you get close to 0. So coming in from the right, you can see that those y values are also approaching 0.16 repeating. Again, when we get to 0, it's undefined, but that doesn't matter to the limit. So this is simply a graphical representation of what we did algebraically in our problem. And let's look at another example. Here we want to guess the value of the limit as x approaches 0 of sine x over x. Again, we're going to use a table to see if we can figure out what y is approaching. As x approaches 0 from the left, we're going to use negative 0.01 again, negative 0.001. These are good choices for numbers that are close to 0 from the left. And then we need symmetric values coming in from the right, which would be positive. And again, on our calculator, we need to make sure we're in radian mode since we're using a trig function this time. We're going to say sine of negative 0.01 over negative 0.01. And this is 0.99 Lots of nines, almost 0.9 repeating. So I'm going to put 0.999. Let's see if we get even more nines repeating if we add an additional 0, making us even closer to 0, and we do. So this appears to be 0.99 repeating coming from the left. Let's see what happens as we come in from the right. Editing our value to get rid of the negative, we get the same answer. Okay, so it appears that we have symmetry coming in from both sides. So what does it appear that we are approaching? Well, 0.999 repeating is going to be 1. So this limit appears to be 1. Evaluating with a table, let's check it with Desmos. All right, in Desmos, with our function sine x over x, we can see that as we approach 0 from the left, we're approaching a height of 1. And as we approach 0 from the right, we are approaching a height of 1. Let me re-emphasize that at 0, the function is undefined, but the limit doesn't care. The limit only cares about what you're getting close to as x approaches, in this case, 0. All right, the next concept in this lesson we need to look at is something called a one-sided limit. And if we zoom in on our limit here, I want to illustrate what you're looking for. This sign that looks like a minus on the exponent of a, what that indicates is approaching a from the left. So this would be read, the limit of the function as x approaches a from the left is equal to L. And I bet you can guess what happens if this negative is a plus. Yes, it means that we're approaching from the right. So when there's a minus up here, it's called a left-hand limit. And if there's a plus, then it's a right-hand limit. And so you can have limits that approach from the left and the right. And then if we read on, it says that the limit of the function as x approaches a, can you see that? That's just a, exist. This limit exists if and only if the limit from the left is L and the limit from the right is also L. So the only way that the actual limit can exist is if you approach the same height from both sides of A. And we're going to look at an example of that. So the example we're going to look at, it says find the limit as x approaches 0 of 1 over x squared. So the 1 over x squared, that is our f of x, and we are approaching a value of 0. Now if you look ahead down here, it says that it does not exist. Let's go to Desmos and get an idea why. So here I have my function graphed. We're approaching 0. From the left, can you see that we're approaching really large numbers? Okay, so if I scrunch my graph to alter the scale, we can see that as we approach 0 from the left, the graph appears to just be going up to infinity. Now the left-hand limit would be positive infinity, but infinity's not a number, and the limit needs to be a number for it to exist. And the limit coming in from the right is also going to positive infinity. So we could say that as x approaches 0 from the left, y can be made arbitrarily large positive, meaning that if we get close enough to 0, the y is just going to get, well, infinitely high. And approaching from the right, the y is also getting arbitrarily large positive. So this is why the limit at 0 doesn't exist. Even though we're approaching the same height from both sides, which is positive infinity, since infinity is not a number, then the limit doesn't exist. And there, I'm going to pause on that for a second so that you can see what they say about the solution. And this is the textbook explanation for why the limit doesn't exist. All right, next concept, intuitive definition of an infinite limit. So this time we're talking about infinite limit. It says the limit as x approaches a of some function is infinity, which is kind of what we just hinted at in the previous example, that if you make x close enough to a specific value of a given function, that it can approach positive infinity. In other words, the y can get infinitely high sometimes as you approach a particular x. And the example that the textbook shows is the example that we looked at previously. So what you need to get out of this is that the limit of a function can approach infinity, but that doesn't mean that the limit exists. It simply means that it gets infinitely high. But in order for a limit to exist, technically it has to approach a specific value. And infinity isn't a specific value. And then the last thing I would mention as far as this lesson goes, if you need additional practice, go check out maybe some other YouTube videos or go look at some of the exercises in this section. And that's going to do it for this lesson. So if you have any questions or comments about anything covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.